Hello, me, Gary Parker here. We're going to play around with percents for elementary school teachers. So, let's get busy. Definition. What's a percent? 50%, 20%, 30%. What does it mean? Well, per usually means divide. Cent means 100. So percent means divide by 100. And literally, that's what the symbol means. I mean, think about it, right? Division bar, 0, 0 for 100. So when you see something like 30%, percent symbol literally means divide by 100. Divide 100. So it translates as 30 divided by 100. Now, we can write division in a lot of different ways. We can use the slash. We can use the fraction bar. We can use the crazy divide symbol. I can write. Or we could use the goes into symbol. Now, if I use the fraction symbol, I can rewrite it as a simplified fraction. So 30%, I could say, well, that's just 3/10. 3/10 can easily be changed to a decimal because I just read it correctly. So here's the tenth spot. I need to put a 3 in it. Put 3/10. 3/10. Dividing by 100 is shifting the decimal point 2 places because there's 2 zeros. So decimal was there, move it 2 places, it goes in front of the 3, is where I have it here. So 30% could be called 30 out of 100, or 3 out of 10, or as a decimal, 3/10. Long division is going to yield that decimal value right there. So other examples of percentages, we see them all the time. Now, sometimes percent is part of a whole, in which case the biggest thing you can have is a whole, so one whole is equal to 100%. However, we can't have percent increase. So for example, when you get a raise, when you have to pay taxes, that's above and beyond the base value. The base value would be 100%. So sometimes we need to go over 100%, and sometimes 100% is the limit because that's a whole. Okay? For example, there's a job to do and it needs to get done. There's one job. You can only do all of the jobs. So 100% is the maximum you can do. Okay. So sometimes, for example, you won't get paid for part of a job till you've completed at least 50% of it, or 9% or 8% of it, and you get the full pay once you've done 100% of it. So again, part of a whole is a helpful way to look at it. So we have this idea of a percent, which is some number out of 100. Okay. So I have some number given, and that relates to some part out of a whole. So we talked about proportions before. So any percent problem can be rewritten as a proportion problem if you can identify the percent value, the part, and the whole. Sometimes we start with a number like, say, 1/4. As a percentage, I would need to rewrite that as something out of 100. The question is, what goes in the top? Well, 4 goes in 125 times, so proportionally I could say, if I need to multiply by 25 to get there, I need to do the same thing to the top to have an equivalent fraction. So 1/4 is 25 out of 100. Dividing by 100 is a percent, so that must be 25%. A different number. 0.001. All right. So I read that as slang. The correct reading of that is 1 out of tenths, hundreds, thousandths. So 1 out of 1,000. Now, agreed, that is less than 1 out of 100, right? 1 out of 100 would be 1%. So that means 0.001 is less than 1%. So if you think about this as being a single percent, 1%, 2%, and so on, over here, we're just to the right of that, we would be at 0.1%. So if I were to say divide top and bottom by 10 here, so take 1 out of 1,000, we know that a fraction will be equivalent if we multiply or divide by the same number top and bottom. I'm going to multiply top and bottom by 1/10. Now, when I do that, 1/10 of 1,000 give me 100. 1/10 of 1 is going to give me 1/10. I'm going to choose to write that as a decimal, right? 1/10. Divide by 100 is a percentage, so this must be 1/10%. Okay. Another one, starting with a percentage. Suppose somebody says they have an interest rate at their bank or savings account of 0.5%. Now, here I have a part of a whole of a percent. Percent means divide by 100, so I have 1/2 divided by 100. Division by 100 would be the same as multiplying by 100, right? Multiply by the reciprocal. So I could say as a fraction, it's 1 out of 200. I can do that as a decimal in a couple of ways. I could view 1/2 as 5/10, and then I have to divide by 100. Dividing by 100 is going to shift the decimal point to make this smaller, so the decimal is going to go to the right 2 places because of the zeros. So that would be 0.005. Double check up here. If you were to take this fraction and multiply top and bottom by 5, 5 times 2 is 10, 10 times 100 is 1,000, you would get 5 of 1,000. That's hundreds, thousands. So there's lots of connections between fractions, decimals, and percents, and the bottom line is you have to be very conscious of the percent symbol means divide by 100. So some rules for working with percents. If you want to convert a percent to a regular number, you just convert the percent symbol to dividing by 100. If you want to take a regular number and convert it to a percent, then the trick there is that 1 is 100%. So then you take whatever number you were given, like 0.3, and multiply it by 100%. And what is 100%? It's a 1. So multiplying by 100% is the same as multiplying by 1, so the number means equals the same thing. Now, if I then clean this up a little bit by leaving the percent symbol alone and saying, well, what is 100 times 3/10? I would find that that would be 30, and the percent symbol just hangs out, 30%. So again, percent to a regular number, divide by 100. Regular number to a percent, multiply by 100%. All right, next, we're going to take a look at some applications of percentages in terms of percent change. So we'll look at sale first. So percent off, or percent increase. And let's take a look at a 20% off sale. So if something is priced at, say, $80, then I can find the discount by just multiplying. So if I take my $80 and multiply by 20% as a decimal, 2 times 8 is 16, and then shifting the decimal point, multiplying by 10, get $16. Okay, so you can double check that on the calculator. Find the sale price, I would then have to take the price, subtract the discount. So then I would take my $80 and subtract $16, and then I should get $64. Is the amount that I'm going to pay. Now let's look at that in a slightly different way. Now, the price originally is 100%. Right? That's what you start with. That's the whole. Now we have this discount as a percentage that is 20%. So ultimately we take the price and we subtract the discount to get the sale. if we do that percentage-wise, then what's going to happen is 100% minus 20% is going to give me 80%, and that's what I pay. So what would happen if I took the original amount, $80, and multiplied by 80%? Just 0.8 or 8/10 is a decimal. Well, 8 times 8 is 16. A tenth times 10 canceled. So I'm going to get, 16. 8 times 8 is 64, excuse me. And so I'm going to get $64, which is the same as before. Now, I had to subtract up front and then multiply second. Here, I had to multiply first and subtract second. Now, personally, I find the subtraction from 100 to be easier than a subtraction from 80. So I think often with sales, it's better to say, if you have a certain percent off, what is the percent you pay? And any time that you have a sale or a percent decrease, and let's say that's going to be D%, it's often important to consider the percent you pay. And that's always going to be 100% minus D%. And this can be directly multiplied by the cost to get the end amount. And so whenever you work with respect to 100%, a percent increase or decrease, what you get is what's called a multiplier. And that multiplier can be very handy. So suppose, for example, wrong button, that there was a 20% off sale. Let's stick with 20%. And the sale price is listed as, let's say, $150. What was the original price? Now, the naive approach on this right here, which, I make naive decisions all the time because I don't have all the information, or I think I do, but I really don't, is to say, well, I'll just take 20% of 150 and then add it back on, bump it up by 20%. But the problem is the 20%, right, which as a decimal would look like that, has to be multiplied by the original. And what that's going to give me is the discount, the amount of discount. And then I would have to subtract that from the original. And this is a bit more complicated than it looks. Discount, there we go. Now on the other hand, I could think, well, if there's 20% off, that means I pay 80%. Which means that if I took 80% of the original, then that's the sale price that I'm going to pay. Okay, so I could think about that algebraically as, well, get the multiplier, because that's what's required with the original. You get the end amount. Now the discount is kind of a step in between, so that's a little bit in the way. So this other way of looking at it is very helpful. So 80% of that original, I'm going to call it O, is going to equal 150. So here I can see, and that's an O, not a 0. Bad choice for variable, huh? I can see that if I want to find O, I would have to divide by 80%. So the original amount is going to have to be equal to 150 divided by 80%. And we could work that out in a moment. I just want to show another way to look at it. I could look at this graphically too. So instead of using a square to designate the whole, I'm going to use a rectangle, and that is my best artistic rendering of a rectangle today. Two things to consider. We have percentages to consider, and we actually have dollar amounts to consider. So I'm going to consider 0 to be over there, 100% to be over there, $0 is over here, and over here, this would be the original amount. And what I want to do is I want to take 20% off. So that means I'm going to chop something off of that original dollar amount. So 20% off is right here. So if I took 20% off of 100%, then that means this must be 80% right there. And 80%, again, that's a percent, is going to mean the same thing as $150 on this side of the scale. Right, so I can show two different scales, the percent scale and the dollar scale. So if I know there's 20% in this region over here, well, there must be 80% over in this region over here. So it's the percent symbol. Now 20 works out kind of nice in this case because I can say, well, let's just keep chopping this up in chunks of 20%, right? 20, 40, 60, 80% right there. So there's 4 chunks that are going to give me $150. And so one more chunk gives me the extra. So I just have to figure out, well, what is a chunk worth here if 150 lies there? Well, that's pretty simple. I just take 150 and divide it by 4. So half of 150 would be 75. And half of 75 is going to be 37.5. So each one of these chunks is worth $37.5. So 37.50 is one of these chunks at 20%. Right, 20, 40, 60, 80, 100. 4 of those chunks give me the 150. So that means I'm just missing a chunk of 37.50. So the original price must be 50 plus that 37.5. So adding those up, I get 187.5. Let's see here, calculator. I want to know what 80% is. Right now, I want to know what 150 is divided by 80%, which is the formula technique that we derived earlier, and there's $187.50. So there's a lot of ways to think about percentages. We have percent decrease. We have percent decrease as a multiplier when we take it away from 100. And we can draw pictures. And the pictures work out nice some of the time, but it kind of depends on the percentage and the number, right? Because you can see here that I had to take this 20% and I had to do some splitting up down here. And then I had to split up that dollar amount and then figure out how to recombine it. So there's no great way to do these. They're all challenging. In some ways, percentages are easy if it's just a direct application, but in other ways, we have to figure some stuff out. All right. Let's see what we got next. All right, visual percentages. That's what we just did. Let's try another example. Suppose we have percent markup, percent increase. Examples of that are tax that you pay on something, getting a raise, or maybe you want to store and you buy something wholesale and you have to sell it retail, which means you have to mark it up a little. So let's suppose we run a 50% markup on the things we take in. Spell, yeah. So that means I buy something. Let's say I bought something for $1. And then I add on a markup, 50% of that is going to be 50 cents. That means I'm going to sell it for $150. Oh, sorry, $1.50. So this right here is the wholesale price. I'm going to call that WS. This right here is my markup. And then over here is the selling price. So my wholesale price, that's 100%. That's what I started with. I have my markup as 50%. That means I sell things at 150% of what I buy them at. When I use 100% as a base and I add a certain from that, what I end up with here is what's called the multiplier. Now it's called a multiplier because I can directly multiply by it to get the selling price or the future amount in this case. So let's take that we have a wholesale value for something $75. We have percent markup, 50%. So that means my multiplier is 150%. As a decimal, that's going to be 1.5. Percent is divided by 100, which shifts the decimal point twice. So 1.5 and 150% are the same things. So to get the selling price, I would just take my $75 starting wholesale price and multiply it by 1.5. And calculator would be nice for this one. So we have $75. Let's blow that up a touch. Go. Times 1.5. So I get $112.50. So just double check that. Sometimes we would just take the slow route, take 75, multiply by 50%, 1.5, and then we would add that on to that $75 we started with. So we have the amount of markup plus the original. And so then there's our $112.50. All right, suppose though, go the other way, that we know the selling price. Let's say something is going to sell for easy $100, and we know the markup, and let's go with how about 25% for the markup. Now the problem here is I don't know the original amount. Now remember, we can change this into a multiplier by adding it on to 100%. So that'd be 125%, or as a decimal, 1.25. So what I know is that if I knew the wholesale value and I multiplied it by 1.25, then that's going to give me the $100. So I could solve this by just dividing by 1.25. So the wholesale is going to be 100 divided by 1.2. And we can plug that into a calculator and get the answer. Well, let's look at it graphically also. We start off with a bar that represents our 100%. Now here I need to go beyond that. So this is going to require a little artistry. So 100% is there. I need to increase it by 25%. So let's see, we need to find what 25% looks like if this length right here is 100%. So 50% would be right there. 25% would be right there. So I need to increase by that distance right there. So let's estimate that distance about that far. That looks good. So that right there would be 125%. Okay, so that's my 25% markup. Now each of these chunks are also 25%. Now let's see, where does the $100 live? Well, the $100 is the selling price. That's including the markup. So over here is where that lives. So I have $100 in there. But this tells me that I need to break that $100 up into 1, 2, 3, 4, 5 equal chunks. So if I take 100 and I divide that by 5, then I should get 20. So that means each of these chunks should be worth $20. $20, $40, $60, $80, and $100. So that tells me that the original price must have been, the wholesale price, excuse me, must have been $80. And we can check on a calculator what is 100 divided by 1.25. So 100 divided by 1 and 25 hundredths gives me $80. It works out nice. Now, what's the point of doing this so many different ways? Well, with little kids, we can pick the problems carefully so that we can always draw pictures to solve them and use some simple multiplication and division to work with it. With older kids, we can start getting into the idea of variables and multiplication and division undo each other and solve things with a more algebraic technique. So we always have multiple approaches to these kinds of problems, which is kind of fun. All right, next on our agenda, Simple interest and compound interest. So simple interest is a legal definition. And it basically says you have some starting amount, you have some interest rate, and you have some time that's elapsed. Now the rate and the time are related to each other. Often the rate will be given as what's called an APR, which is an annual percentage rate. So that means the rate applies to a whole year. If that's the case, because of the annual, then time should be measured in years. Now, simple interest is what generates compound interest, and I'll demonstrate that in just a sec. Now, compound interest is a little bit more complicated. That means your interest collects interest. So you have some initial amount, 100%, and you add on to that some modified rate. And you keep doing that over and over again. So this base amount right here I have in parentheses is what's called that multiplier that we talked about earlier. So just establishing a few variables here, F is the future value, so some dollar amount. P is the present value, or the principal, or the balance. R is generally an annual percentage rate. N is the number of times per year you get interest, which is the idea of simple interest. And T is just the number of years that have gone by. We'll look at an application of simple interest and we'll turn that into compound interest. So if you think about credit cards, you're going to have some percentage rate. So let's just say that your APR on your card is 12%. Now, it doesn't usually work that you borrow some money and you wait till the end of the year to pay it. Typically, the loan contract says you have to pay monthly. Now, you can usually pay earlier than that if you want. You could send in a payment every week if you like. And what happens is, to figure out how much interest you owe, the bank's just going to take whatever your current balance is, consider your interest rate, and how much time has elapsed. Right? Well, let's just say 1 month has elapsed. If 1 month has elapsed, then that means time, because I have an APR, must be in years, must be 1/12 of a year. Now, technically, that's not quite accurate, but we're just going to go with that because it's easier. Let's say your principal, your starting amount, is maybe you borrowed $1,000. So we have our rate, we have our time, we have our principal, so we can calculate our interest by just taking our $1,000, multiplying by 12%, needs to be a decimal or a fraction, and multiply by time. Now, order of operations, multiply left to right, but multiplication is nice. You can do it in any order you want. 1/12 is kind of nice because that is 1%, right? Which we prefer to write as a decimal here, which is going to be 100. And then I have to multiply that by 1,000. Well, 1% of 100 would be 1, so 1% of 1,000 should be $10. Is what I owe them. Now, so what happens is I send them my money and they say, hey, you owe me $10 right up front, and then like maybe I sent them $100, so that means 90 goes to reduce my balance here. Okay. But they have to use simple interest to calculate what's happened in that time frame based on the APR. Now, in reality, what happens is they look at the number of days in the month. So if this was February, they would calculate 28 of 365. And technically, it's a law. They don't have to actually use 365. They could use 360 if they wanted to. and they can use any whole number from 360 to 365. And the reason is, on average, there's about 30 days in a month, and there's 12 months. Well, 30 times 12 is 360. So sometimes they like the ease of calculation of using 360 and 12 months in a year. On the other hand, there are 365 days, technically 365 and a quarter, but that's not in the law. So they can either use 1/12 or 28 out of 365, or if it was October, they would use 31 out of 365. So it just kind of depends on the month. April would be 30 out of 365. All right, so does simple interest turn into compound interest? So here's how that works. So let's look at an investment instead. And since we're investing, let's use blue. So somebody promises to pay you 12% APR. Now, dividends can be paid on investment, and a dividend just means they send you the money. So you give them $1,000 at the end of the year. They say, hey, here's 12% of the $1,000. They keep your $1,000, and next year they give you another 12% of your $1,000. And you just keep getting 12% of $1,000 over and over again. That's a dividend. Other investments like savings accounts and annuities get to add that interest back into your account. So what will happen is the table here, time versus money. So initially, let's say you throw in $1,000. After 1 month, what's going to happen is they're going to say, well, cool, you have $1,000 in our account, and we owe you 12% on that, but only 1 month has gone by, so then they're going to multiply by 12, and then they're going to add that back onto your account, which had $1,000 in it. All right, so that is 1% of 1,000, which is $10. So now you have $1,010 in your account after 1 month. What happens on the next month? Well, the second month, you have interest, right? So after a month, that $1,010 has been sitting there, and they do the same thing. They multiply that by 12%, but they discount it because it's only 1/12 for the year, and that's the annual rate. And they add that back onto what was in your account, which is $1,010 for that previous month. Right, and so we can do the math, figure out what that is. Calculator time. Actually, I can do that without a calculator. 1% is 1 out of 100, shifts the decimal place 2 places, so I get $10.10 added on. That's going to give me $1,020.10. And then I just keep doing this over and over again. I want to see what's going to happen after a year. Well, the thing that's going to be helpful here is the $1,000 is the same here and here. Here I have 1,010 is the same there and there, but otherwise the procedure is the same. I'm going to take this base amount, which is a monthly rate. So let's take a note that we're going to take that APR, we're going to turn it into a monthly percentage rate, which is 12%. 12 over 12 is 1%, so it chills out there. The 1,000 or the 1,010, that's 100% of what I started with. So if that's my monthly rate, then my monthly multiplier is going to be 100% plus 1%, or 101%. So my claim is that that 1,010 is that $1,000 times 1.01%. And this 1,020 is that 1,010 times 101%. Now, keep in mind, though, that this $1,010 came from that expression right there. So I can do a little substitution. So what that's going to give me is that this $1,020.10 came from starting at $1,000, multiplying by 101% once, and then multiplying by 101% a second time. Guess what's going to happen in the third month? Well, that $1,000 I started with is multiplied by 101% in the first month, and then another 101% in the second month, and then another 101% in the third month, which can be more concisely written using exponents, which is $1,000 times 1.01 to the power of 3. So what about the 12th month? Exactly $1,000 times 101% to the power of 12. What about a calculator? See what we got. So I'll check the second month, and then we'll see what the 12th month is up to. So if I take that $1,000 starting point and I multiply by 101%, a regular number, and raise that to the power of 2, then I'm going to get that $1,020.10 that I calculated the slow way earlier. Figure out what happens in the 12th month. I take my $1,000 and multiply by 101%. And I do that multiplication 12 times, which means I have 12th power. And I'm going to get $1,126.83 if the bank can round up, which they have the choice not to. Legally. Weird. Anyway, so think about it. 12% of 1,000. So again, this was $1,126 and was it 53 cents? 83 cents, excuse me. Now, if I just did simple interest on this and I didn't let my interest collect interest, simple interest says I is 1,000, your starting amount, times your rate, 12%. So let's write that as a decimal. Although many calculators do allow the percent symbol these days, it's quite nice. Times 1 year. Now, 12% of 100 would be 12, so 12% of 1,000 would be 120. So by collecting interest each month instead of just at the end of the year, I'm $6.83 better off. Well, that's just on $1,000, right? What if I put in 10,000 or 100,000? So that saying that money makes money, that's kind of a compound interest reference there. All right, so again, this formula right here that I ended up with is related to the formula I stated back on this page right here. So let's take a look at that again. So compound interest gives me a future amount based on some present amount, an annual percentage rate, the number of times I collect interest each year, and the power is n times t. So for the problem I looked at, I had $1,000 for my principal. My annual percentage rate was 12%, or 12/100ths, and I was collecting interest 12 times a month. N is 12, t is time. So this would be an expression here for any time in the future where t is the number of years that have expired. And it could be a fraction of a year, or a whole year, or multiple years. So if we plugged in 1 year there, we would get that number we got earlier. We could plug in 2, and so on. So why is this n here as a variable? Well, you could collect interest monthly. You could collect interest daily. And you might notice that some credit card contracts talk about the average daily balance, and they actually charge you interest daily instead of monthly, in which case we'd have to mess around with 360 or 365 and the days in the month. So this gets a little more complicated, but still the same formula. You could collect interest quarterly, which is a lot of investments do quarterly interest. It could be biannually, it could be semi-annually. There's lots of possibilities. And it just depends on the terms of agreement that you set into with your bank or financial institution. But this is the basic formula for compound interest. So that's it for now. I hope this helped in your knowledge of percents. Take care, do good math, have a great day.